Okay, so Bismillah ar-Rahman ar-Rahim. Next we have service road. So this is the service road. Service roads are provided on canals for inspection purposes and may simultaneously serve as the means of communication in remote areas. They are provided zero point 0.4 meter to 1 meter above the full supply level depending upon the size of channel. So service roads, these are provided on canals for inspection purposes and may simultaneously serve as the means of communication in remote areas. So you might have seen that when we have canals, so at the side of the canal commonly roads are constructed. So these are known as service roads. Next we have dowla or dowel. In some irrigation books they say dowla or dowel. In other irrigation books they call it as a dowel. So dowel is a measure of safety in driving with side slopes of 1.5 to 1 to 2 to 1 are provided along the banks. So this dowla or dowel, these are provided as a measure of safety to the vehicles that will be moving on this service road. Clear? The top width of dowla is kept from 0.3 to 0.6 meter and is 0.3 meter above the service road. Next is spoil bank. So this is spoil bank. When the earthwork in excavation exceeds earthwork in filling, the extra earth has to be disposed of economically. When we are constructing an irrigation canal and the earthwork in excavation exceeds earthwork and filling, so we have the extra material left, so that extra earth has to be disposed of economically. So economical mode of its disposal may be collecting this soil on the edge of the bank embankment. So just collect it on the edge of the bank embankment itself. Longitudinal drains running by their sides are excavated for the disposal of rainwater. So you can see here, now we have the spoil bank. So if there is rain, water will accumulate here. So in order to drain this rainwater, these longitudinal drains are provided. And at intervals, transverse drains will also be provided to drain the water out. So this is spoil bank. Clear? Next we have burrow pit. When the earthwork in filling exceeds the earthwork in excavation, the earth has to be brought from somewhere. Now in this case, the earthwork in filling exceeds the earthwork in excavation. So we have to bring additional material from somewhere. The pits which are dug for bringing earth are known as burrow pits. So such pits which are dug for bringing earth, these are known as burrow pits. If such pits are excavated outside the canal or channel, they are known as external burrow pits. Just like you can see here outside the channel, so it is outside burrow pit. And if they are excavated somewhere within the channel, they are known as internal burrow pits. Also you can see here that we have this inside borrow pit or internal borrow pit. They are excavated at the bed of the channel or canal. You can see here that these pits are excavated, and then this material is used in filling. And you can see here that these pits, they have this spacing L by 2. Then again at the center of the bed of the canal, another pit. So these are internal borrow pits. Internal borrow pits are more preferred than external one. The inside borrow pit may be located at the center of canal. So they may be located at the center of the canal. The idea behind this is that the borrow pits will act as water pockets where the silt will be deposited, and ultimately the canal bed will get leveled up. So what is the idea behind this borrow pits here inside the bed of the channel? That these will act as water pockets, because the water that flows in the channel or canal carries silt. So as the water stays in these pockets, the silt will be deposited, and with the passage of time, ultimately the canal bed will get leveled up. So these are borrow pits. Clear? We borrow the material that is required to use for filling in case when we have earthwork in filling exceeds the earthwork in excavation. Next we have bake berm or counter berm. Even after providing sufficient section for bank embankment, the saturation gradient line may cut the downstream end of the bank. In such a case, the saturation line can be kept covered at least by 0.5 meter with the help of counter berms, as shown in the figure. Now, even after we provide sufficient section for the bank embankment, still it may be possible that this saturation line, it can cut the sides of the bank, but we have to provide minimum 0.5 meter cover. So for this purpose, this saturation line can be kept covered at least by 0.5 meter with the help of what is known as counter berm. So you can see here with this counter berm here, this is the counter berm. So this saturation line here, this is kept covered at least by 0.5 meter. Next we have balancing depth for excavating canals. A canal section will be economical when earthwork involved at particular section has an equal amount of cut and fill. Usually a canal section has a part in cutting and a part in filling. So as I said before, that this is economical. Clear? If a canal section is such that it is partly in cutting and partly in filling, because the material that we remove for cutting, the same material can be used for filling at other section. So if the amount of cut is equal to the amount of fill, it has to be paid for once only. So if we have canal in filling, then in that case we have to bring the material from outside to fill. So you can see the cost of borrowing the material, transportation cost. If we have more cutting in the canal section, we have to dispose of the extra material take it to other area, for example. So that's why a canal section that will be economical when earthwork involved at a particular section is equal, has equal amount for both cut and fill. Now, definition of balancing depth. For a given cross section, there is always only one depth for which the cutting and filling will be equal. There will be one depth for which the area of cut that will be equal to the area of fill. This depth is known as balancing depth because it balances the two areas, area of cut and area of fill. So this is known as balancing depth. This balancing depth can be computed by equating the areas of cutting and filling. If we can calculate for this section the area of cut and fill, we can estimate, for example, what is the balancing depth. And this is required from economy point of view, because if we have equal amount of cutting and equal amount of filling, so just the material that is removed in cutting, the same amount of material will be used for filling. So we do not have to dispose any extra material from cutting, or we do not have to bring additional material for filling. So let us see that how we calculate this balancing depth. Now in this example, calculate a balancing depth for a channel section having a bed width equal to 18 meter. This is the bed width of the channel, 18 meter, and side slope of 1 to 1 in cutting. Now the side slope of the channel, that is 1 to 1 in cutting and 2 to 1 in filling. So you can see for filling it is 2 to 1. The bank embankments are kept 3 meter higher. So you can see here the bank embankment, these are kept 3 meter higher. Then the ground level, bottom level, and crust width of the banks is kept 2 meter. So this is 2 meter. This is the crust width from here to here. This is the crust width, and this is 2 meter. As you can see here, 2 meter. So now we have to calculate the balancing depth, and it is this D here. This will be the depth for which the area of cut and fill that will be equal. So this is known as balancing depth. So let us try to solve this problem. So first we have to calculate area of cut or area of fill, and then we can equate them to get the value for the balancing depth. So we have area of cutting, so this is equal to area of cut. Now you can see here that we have these as trapezoidal shapes. Similarly, for the filling, we also have trapezoidal shape. So if you know the formula directly for a trapezoidal cross section, that formula we can directly use. Let's say this is the side slope z to 1. We have this as the depth. So in this case, let's say this is d, small d, and this is the bottom width. So we have the formula here. What is the formula for this area. So this is equal to B, the bottom width, plus Z, which is the slope, into D, and this whole multiplied by D. This is the area. So this equation you can use. Now according to this equation here, so you can see here that the bottom width, that is 18, plus we have Z, so Z is 1 here, the side slope is 1:1, so it is 1, Z is 1, and D we have to calculate, so this is D into D. This is square meter. So now if you simplify here, so this will be equal to 18 plus D into D square meter. Even if you do not use this formula, you might have studied there is another way of calculating the area for a trapezoid. You might have studied this in maybe your survey course or other courses. And what is that? You can see here that the top width here, the top width, so this will be still 18 from here to here. This is still 18. Now the slope is 1 to 1. So that's why this will be D, because the slope is 1 to 1. So it means that the depth is a D. This horizontal distance will also be a D here. And similarly, this will be a D. Now to calculate the area, so this will be equal to sum of the bottom width, that is 18, plus we have sum of the top width, that is 18, plus we have D and D, so this is 2D, so sum of the bottom width plus the top width divided by 2, we take average of this, multiply by a D. So you can see here that if you simplify this, so see 18 plus 18 two times and 2D. So basically this 2 cancel out with this 2. So we are left with just 18 plus a D. So this is 18 plus a D into a D. So you can see here that this is the same expression as we get using the formula here. So either you use this formula or this one, you get the same result. Next we calculate for area of fill. So we have area of we have area of fill. Now again we use the formula. So you can see here that this is the filling here. So this is the first area here, and this is the second area. So the dimensions are the same. You can see here, if we can calculate the area of one trapezoid, we can just simply multiply by 2 to get the total area for filling. So this will be equal to 2 plus, what is z? Z is, you can see here, 2 ratio 1. So z is 2, and then the depth is 3. So this is into 3, and this whole multiplied by the depth, which is 3. So this is the area of this one trapezoid here. Now for the second one, because of the same dimension, so we simply multiply this here by 2. So now you can see here, just need to simplify. This will be again square meter. So 3 2s are 6, 6 plus 2, 8, 8 into 2, 16, multiply by 3, so 48. So this is 48 square meter. Now we equate the areas. So equating the areas of cutting and filling. So we have area of cut and equate this to the area of fill. So what was the area of cut? 18 plus d into a d. So this is 18 plus a d into a d, and this is equal to 48. Now we can just simplify. So this will be equal to d square plus 18 into d minus 48 equal to 0. So this is now quadratic equation. You can see here that this is quadratic equation. It will have two roots. So just solving, either by quadratic formula or by equation solver, we will get two roots for the depth d. That will be equal to, one root is plus, that is 2.357 meter, and the second root is negative minus 20.357. Since negative depth is not possible, so balancing depth, that is equal to D is equal to 2.357 meter. So this is the depth which will equate the area of cut with fill. So this is how we calculate the balancing depth. This is the balancing depth. Next we discuss design of unlined canals. The design of unlined canals which will remain stable is an important challenge for hydraulic and irrigation engineer. Unlined canals, you can see here we defined them, will remain stable. It means that there is no silting and no covering, because in case of silting, the discharge carrying capacity that will be reduced, affected. In case of covering, removal of material, the shape will be distorted. So design of unlined canals which will remain stable, this is an important challenge for hydraulic and irrigation engineer. The solution of the problem consists in determining depth, bed width, side slopes, and longitudinal slope of the channel so as to produce a non-silting and non-covering velocity for a given discharge and sediment load. Clear? So how to solve this problem? The problem solution consists that we determine the depth, the bed width, the side slopes, longitudinal slope of the channel such that will produce a non-silting and non-covering velocity for the given discharge and sediment load. So how to do it? An empirical approach to find a stable section that will be non-silting and non-covering was based on the analysis of data observed for canals which were flowing in regime. Regime again means stable section. No silting, no covering for many years. So what was the situation? That an empirical approach means that we develop a formula from the data. We have the data and we just do the regression analysis and we develop the equations. So empirical approach to find a stable section for a canal that will be not silting nor covering was based on the analysis of data observed for the canals which were flowing in a regime for many years. So those canals for many years, no silting, no covering, we collect the data and then from there data equations were developed. Empirical relations between velocity, depth, hydraulic radius, and slopes were found to determine a stable cross section. So the relationships that were developed in the Indo-Pakistan subcontinent are based on Kennedy's silt theory and Lacey's regime theory. So these two theories are specifically mentioned in your syllabus. So this Kennedy's silt theory and Lacey's regime theory, these are used for the design of unlined canals. We also have design of lined canals. So for the lined canal, the same approach applies as you studied in your hydraulics course. You use the Manning's equation, the Chesy formula, and then you have the most efficient cross section, etc. So that approach is used for the lined canals. Now for the unlined canals, how to design them? So as per your syllabus, these two theories we will study in detail: Kennedy's silt theory and Lacey's regime theory. There are also other approaches, but as per your syllabus, we will study these two theories in detail and how to design the unlined canals. So we start with Kennedy's silt theory. So R.G. Kennedy, executive engineer, Punjab Irrigation, in charge of the Upper Bari Doab Canal, published his work in 1895 through the Institution of Civil Engineers, London. So he was an executive engineer, XN, in Punjab Irrigation, and this was in British India before partition. Clear? You see, 1895. Then he published his work. So he was in charge of the Upper Bari Doab Canal, which is in Punjab, Pakistan. Kennedy selected 22 sites. If you study book by Dr. Iqbal Ali, 20 sites are written. For other books, they write down 22 sites. So Kennedy selected 22 sites on Upper Bari Doab Canal for carrying out investigations about velocity and depth of the channel. So he selected these 2022 sites for carrying out investigations about the velocity and depth of the channel. He collected the data. The sites selected by him did not require any silt clearance. So these were stable sections which did not require any silt clearance for more than 30 years and were thus supposed to be flowing with non-silting and non-covering velocity. So these 22 sites which were selected by Kennedy, so these sites on the Upper Bari Doab Canal, which is in Punjab in Pakistan, they did not require any silt clearance for more than 30 years. So these sites were supposed to be flowing with non-silting and non-covering velocity. So according to Kennedy, the vertical eddies generated from the bed of the channel support the silt in suspension. What Kennedy theory says that the water is flowing in a channel. So along this bed of the channel, as the water flows, we have unlined canal, so there will be friction. And because of the friction, these eddies will generate. Clear? And these eddies will keep the silt in the water in suspension. These eddies will not allow this silt to settle down. Some eddies may start from the channel sides, but these are for most of its part horizontal and do not have any silt supporting power. According to Kennedy's theory, this is what the Kennedy's theory says, that there may be eddies here from the sides, maybe eddies generated from the sides, but for most of its part, these eddies are horizontal and so do not have any silt supporting power. The silt supporting power of the stream is proportional to the bed width and not the perimeter of the channel. So this is according to the Kennedy's theory, that these eddies, vertical eddies, which are generated at the bed of the channel, these have the silt supporting power. They keep the silt in the water in suspension, not allow it to settle. This is required, because if the silt keep on settling, then this is not desirable, because it will, in the long run, it will affect the discharge carrying capacity of the channel. So according to this theory, the side eddies which are generated from the sides do not have silt supporting power. So according to the theory, the silt supporting power of the stream is proportional to the bed width and not the perimeter of the channel. So because from the sides, the eddies do not have silt supporting power, so according to him, that only eddies generated at the bed of the channel, they keep the silt in suspension. So that is why the silt supporting power of the stream is proportional to the bed and not the perimeter of the channel. This is according to this theory. Kennedy defined critical velocity as non-silting, non-covering velocity, and give a relationship between the critical velocity to the depth of flowing water. So based on the data that he collected from the sites of the Upper Bari Doab Canal, he come up with these empirical equations. And he defined this as the critical velocity that is non-silting and non-scouring. This is the velocity with which the water should flow in the channel. That will not allow the silt in the water to settle, neither it will cause the erosion of the bed or side material, scouring. So this was related through this equation to the depth of water. And in the FPS system, this is the equation. So V sub naught, that is the critical velocity, and D is the depth of water. Now this equation was developed on the basis of observations on one canal only, because these sites that were selected on the Upper Bari Doab Canal. So these equations, if we want to determine the critical velocity, which will not be causing silting and scouring in the channel, so it is applicable only to those channels which are flowing in sandy silt of the same quantity or grade as that of the Upper Bari Doab Canal system. So if any other place where we want to construct a canal, if that silt quantity and grade, that is of the same is the Upper Bari Doab Canal, only then we can directly use these equations. Only then we can use directly these equations. Since it may not be the case, so Kennedy introduced another factor m into this equation. That is known as the critical velocity ratio, was introduced to account for the variation of the silt grade from the standard conditions of the Upper Bari Doab Canal. So he modified this equation. So according to this equation, now V is equal to 0.55 m into D power 0.64, where this m, this is known as the critical velocity ratio. This was included to account for the variation of silt grade, because we may not have the same silt grade everywhere. So this is the formula in the FPS system. Now in this equation, this m, that is given as V divided by V naught, this is the critical velocity ratio, where V is the critical velocity for relevant silt grade of area, and V naught is the critical velocity for the silt grade for Upper Bari Doab Canal system. This is the critical velocity ratio. Now, sand coarser than the standard silt at Upper Bari Doab Canal was assigned the values of m from 1.1 to 1.2, and that finer than the standard. Standard means that in the Upper Bari Doab Canal from 0.9 to 0.8. For silt of Indus River in Sindh, m is equal to 0.7. So in general form, this equation for critical velocity that Kennedy gave can be written as V sub naught equal to C into D power this n. So in here you can see V naught is the critical velocity, D is the depth of water, C is a constant, and n is index number. Now we have different types of silt grade. You can see here we have coarse silt. If we have coarse silt, then in this equation the value of C should be then 0.7. If we have sandy loam silt, then it should be 0.65. This is here in this equation. Coarse light sandy silt, then 0.59. Light sandy silt 0.53. So these are guideline values, clear. And the critical velocity ratio for these silt grades can be for coarse silt 1.3 and so on. No separate formula was suggested by Kennedy for fixing the longitudinal slope. You can see here the longitudinal slope, that is important parameter. See in the Chezy formula, V is equal to C. When we discuss the velocity, let's say we check the Chezy formula, if you remember from your hydraulics course, we have this R into this S. This S is the longitudinal slope, so it is important parameter. Now, in the Kennedy's theory, later on we will discuss the drawbacks of the Kennedy's silt theory, but at the moment we just introduce the basic concept and how to design a canal according to this theory. Later on we will study the drawbacks in this theory. So Kennedy gave no separate formula for fixing the longitudinal slope. So it means that if you change the longitudinal slope, you will get the dimensions of a new cross section. It means that we do not have a unique solution. So this is the drawback in the Kennedy's theory. And the Chezy formula and Cutter formula to determine the C in the Chezy formula, these equations, these were used. Because you see that at that time, when Kennedy's developed these equations in 1895, so those equations were available to him at that time. So he used the Chezy formula and the Cutter's formula to calculate the C in the Chezy formula. These equations were used by him. So this is the Chezy formula, and this is how we calculate the C in the Chezy formula using the Cutter's equations in the MKS system and in the FPS system, where C is the flow resistance factor, S is the longitudinal slope of the channel, R is the hydraulic radius or hydraulic mean depth, and N, this is known as the rugosity coefficient. This is the roughness coefficient. So this is in irrigation books known as the rugosity coefficient. So you can see here that this rugosity coefficient, it depends upon the channel conditions. If the condition is very good, then the value of N is 0.0225. For good condition, 0.025. For fair condition, 0.0275. And poor condition, it can be taken as 0.03. These are guideline values. Now, in the hydraulics course that I teach, I actually teach that how we can estimate these values, like for example the Manning's roughness coefficient. So for any given channel, so these are actually determined. Clear? No relationship for ratio of B and D was provided. You see here, this is another drawback of the Kennedy's silt theory. In order to calculate the section of the channel or canal, the following must be known. If we want to design a canal cross section according to the Kennedy's theory, then this data must be known to us. The discharge must be known to us, the rugosity coefficient, the critical velocity ratio, and the longitudinal slope of the channel. So this data must be known to us. So it is then possible to fix the area of cross section by assuming side slopes. Side slope we will assume for the cross section, determining the breadth and the depth. It may be noted that to carry the same discharge with the same sediment load, we may have a number of combination of slope. So you see the slope here is assumed. Actually, practically, then it will depend on the ground where we have to construct the canal. From there, we have to calculate practically. So anyhow, but if this value changes, what will happen? We may have a number of combination of slope, bed width, and depth, and that choice of the best section may become difficult. So these are actually the drawbacks in the Kennedy's theory that were that were addressed in the Lacey's regime theory that later on came. So how to design the canal according to the Kennedy's silt theory? The design procedure, we have different cases. So case one is when discharge, rugosity coefficient, critical velocity ratio, and the longitudinal slope are given. So we have a step-by-step procedure. Step number one is that assume a trial value of the depth. So you can see here that the Kennedy's theory, it is essentially a trial and error procedure. First, we have to assume the value of the depth. Now it should be realistically taken in order to reduce the number of trials. Step number two, calculate the critical velocity using the Kennedy equation, which he gave this equation. You see the depth we assume in the first step, the critical velocity ratio that is given. So we can calculate the critical velocity. This is the velocity. If we have this velocity in the channel, the water flows with this velocity in the channel or canal. It will not cause silting, neither it will cause scouring. So we have in the MKS system and also in the FPS system. Then step number three is that discharge is given and we have calculated this velocity here. So we can calculate the area A. This is the flow area of the channel. So we can calculate this area by dividing the discharge by the velocity. Step number four is that knowing the depth and the area, now we can calculate the bottom width of the channel. Now the side slope will be assumed for the channel cross section. So in the irrigation books, they say that for alluvial soil, it is assumed to be 1/2. So that's why in most of the book, when you see the procedure, they assume the side slopes for alluvial soil can be taken as 1/2. So when the side slopes are assumed as 1/2, then this is the formula for the flow area. Now in this, you can see here area we calculate in step number 3, and the depth that we assume in the step number 1, the only unknown is B. So now from this equation, the bottom width of the channel that can be calculated. Step number 5 is calculate the wetted perimeter and the hydraulic mean depth, that is the hydraulic radius, by using this equation that you have already studied and should remember from your hydraulics course. So this is the wetted perimeter, and once we know the wetted perimeter, we already know the area, so we can calculate the hydraulic radius or hydraulic mean depth. Now step number 6 is that we will calculate the actual mean velocity of flow from the Chesy and Cutter equations. Now we have the hydraulic radius, we have the rugosity coefficient, clear, we have the longitudinal slope, so we can calculate the Chesy C from the Cutter equation, and then in the Chesy formula we have the C, we have the hydraulic radius, we have the longitudinal slope, so we can again calculate the actual mean velocity. If this velocity is the same as calculated in step number 2, that is the critical velocity. This is the critical velocity which is non-silting and non-scouring, which is required. So we now calculate this actual mean velocity. If this is the same as in step 2, then the assumed depth is correct. No further trial is required. The assumed depth is correct and we get the dimensions for the canal. But if this velocity is different, so it means that it is not desirable, because it will, if it is less than the critical velocity, the material will be deposited. If it is, for example, more than the critical velocity, then it will cause scoring. So this will not be desirable. Then what we do, if different, then repeat the calculation with new assumed value for the depth till the two velocities are the same. So this is a trial and error procedure. So let us try to solve one problem on this, how we apply this Kennedy cell theory to design an irrigation canal or channel with the following data. So the given data is that discharge is 30 cubic meter per second. The longitudinal slope is 1 in 5,000. The rugosity coefficient, that is 0.0225, and the critical velocity ratio, that is 1. So how we use this theory to design the irrigation canal? Now let us try to proceed the step-by-step procedure that we just discussed for the design of irrigation channel by the Kennedy theory. So step number 1 is we will assume the value for the depth. So step number 1, we will assume a depth. So it is a trial and error procedure. So assume a depth, take realistic values so as to reduce the number of trials. Now let us assume the value of a D here. For example, we start with, let's say, 2 meter. So this is the first assume value. Now step number 2 is we will use the Kennedy equation for the critical velocity. So we calculate the critical velocity. So what is the equation for that? That is the Kennedy equation. We have this V that is equal to 0.55. Take care of the system of units. 0.55. Actually, in some books it is 0.546. So it is rounded 0.55 into m, the critical velocity ratio, into the depth. So this is power 0.64. Now just need to put values here. So m and depth, we can calculate the velocity here. So this will be equal to 0.55 into 1. M is 1 given here, and depth is coming from step number 1. We assume this is 2, and this is power 0.64. So we will calculate the critical velocity here. Now this comes out to be 0.857 meter. 0.857 meter per second. Next we go to step number 3. Now we have this velocity here, and the discharge is given. We can calculate the area A. So calculate the area. So for that we have this area A, that is equal to the discharge which is given divided by the critical velocity that we calculated in step number 2. So the discharge, that is 30, and the velocity, that is 0.857. So we can calculate the area. So area comes out to be 35 square meter. 35 square meter. Now we have the area, we have the depth. So we can estimate the bottom width of the channel section, that is step number 4. So we can calculate the bottom width. That is B, but because it is trapezoidal channel, so we have to assume the side slopes. So assuming, as it is already given, that for alluvial soil we can assume the side slope, that is Z ratio 1 is half ratio 1. So now you have the formula. In that case, area A, that will be equal to B into D plus D square by 2. When we take Z as half, so then it will be equal to Z square by 2. This is then the formula. Now you can see that in this formula A is known, which is 35 square meter. D we already assume in the first step. So the only unknown is B. We can now easily calculate B from here. So we already know that we have 35 as the area. B is unknown, which is the bottom width. Our depth we have already assumed 2, and a D square by 2. So it is 2 square by 2. So now from here we can calculate the bottom width. So B, that comes out to be 16.5 meter. Now we have the dimensions, the side slope, the depth, the bottom width. So we can go to step number 5. Step number 5 is to calculate the wetted perimeter. And hydraulic mean depth or hydraulic radius. So for the wetted perimeter, This is the equation: b plus d into square root of 5. The side slopes we have already assumed. So this is the equation. Now just need to put the values for the b and d. So the wetted perimeter comes out to be 20.97 meter. 20.97 meter. Now we can calculate the hydraulic mean depth or hydraulic radius. So that is equal to area A divided by this wetted perimeter. So we know that the area is 35 square meter. And the wetted perimeter we just calculated 20.97. So this will give us the hydraulic radius. This is 1.67 meter. So now we have the hydraulic radius, so we can go to the final step, that is step number 6 of the design procedure. So we use the cutter equation. Or formula, calculate the C in the Chesi formula. So the cutter equation and the Chesi equation. So the cutter formula C, that is equal to 23 plus 1 by n. N is the rugosity coefficient which is given, plus 0.00155, and this are divided by the slope, longitudinal slope. This are divided by 1 plus 23 plus 0.00155 divided by the longitudinal slope into n divided by square root of r, the hydraulic radius. So if you plug in the values, the value of C comes out to be 48.974. So it is a constant, no units, 974. Now we can use the Chesi formula. So V is equal to C into square root of RS So we have all the values clear. In this case, you can see that C we just calculated 48.974. So this is 48.974 into R. R we have calculated 1.67. So this is 1.67 and the slope is 1 in 5000. So this is 1 in 5000. So we can calculate this velocity here. This is the actual mean velocity. Remember, this is the actual mean velocity. Now this comes out to be a 0.895. 0.895 meter per second. Now we compare this with step number 2, the critical velocity. So what is the critical velocity? 0.857. So this is actually greater than the critical velocity in step number 2, that is the critical velocity. That is the critical velocity. This is the actual mean velocity, and that is the critical velocity. Actually, the critical velocity that is required because it is non-silting, non-covering. So this is the critical velocity. And what is its value? Its value that we obtained in step number 2, 0.857. 0.857 meter per second. Now you can see that if these values were exactly the same, then the solution will terminate here. And we get the dimensions for the channel section. There the width is, bottom width is 16.5 meter, the depth is 2 meter, the side slopes are half ratio 1, and the other data that is given, longitudinal slope 1 in 5000. You see that this actual mean velocity, it is greater than the critical velocity. So it means that this is not okay. Why? Because this velocity is greater than the critical velocity. So it means that this will cause scouring in the channel, erosion. So that's why the solution continues and we go for second trial. So I will just quickly go through the steps now. For the second trial, we now assume another value of the depth. Now we should increase or we should decrease the value of D. We assume here the value of depth is 2 meter. Now we should increase or we should decrease. Now you can see here that this velocity we want to decrease because it is greater, or you want to increase this velocity because it is smaller. You can see here that V is inversely proportional to the area. Q is divided by area A, that you get the velocity. Now this is the actual mean velocity. I want to decrease it. So it means that I have to increase the area A. So it means that we should increase the depth. Clear? So now we go for step number 1. I will very quickly go through it now. So in step number 1, we now assume the D value now the D value is equal to 2.3 meter. 2.3 meter. Step number 2 is we apply the Kennedy equation. And calculate the critical velocity. V is equal to 0.55 into critical velocity ratio into this depth, power 0.64. So just you put the values directly. we will get this critical velocity as equal to 0.937 meter per second. Next we have to calculate the area. So step number 3. So we calculate the area A, that will be equal to the discharge which is given divided by this critical velocity. So this area comes out to be 32.02 square meter. 32.02 square meter. Next we can quickly calculate the bottom width. So that is step number 4. We already know this equation, the side slope we already assume. So that will be equal to B into D plus D square by 2. The only unknown is the bottom width. So we can calculate the bottom width from this equation, just plug the values. So this comes out to be 12.77 meter. 12.77 meter. Next we go for step number 5. And we calculate the wetted perimeter. So that is equal to B plus D into square root of 5. So just put the values here. This comes out to be 17.91 meter. 17.91 meter. And we can calculate the hydraulic radius. So that is equal to A by P. This comes out to be 1.788 meter. And step number 6, we use the cutter and Manning equation, this Chazy formula. We can also use Manning's equation, but actually in the Kennedy's silt theory, he used the cutter and Chazy formula. So step number 6 is you calculate C according to the cutter's formula. That comes out to be 49.554. And we have the velocity, actual mean velocity, that is equal to, by the Chazy formula, C into RS. And this comes out to be 0.937 meter, 0.937 meter per second. And now we have to compare this with the step 2 critical velocity. Step 2, we have the critical velocity as how much? 0.937 meter per second. 0.937 meter per second. So now it means that the actual mean velocity is equal to the critical velocity, that is non-silting and non-covering. So the condition required, that is fulfilled. So it means that no further trial is required. So the solution terminates and then you can write down that the bottom width of the channel is 12.77 meter. The depth, that is 2.30 meter, and the discharge and other, that has given data, the longitudinal slope, so that is given data. This will be the values for the parameters of the canal section.